Excellent. So while it's running, let's just take a quick look at this worksheet. You had the answers for the worksheet, but again, what we were doing with these right triangles is we were taking these pictures and we were setting up the three right triangles and making them orient the same way so that we could set up proportions to solve for the unknown parts, which really goes back to what we were doing in the previous chapter, looking at that. And that's where we were taking, like I say, so we were taking this triangle and maybe rotating it so it's upright like this. And we take this triangle and we're doing the same thing, rotating it. Oh, where's my rotation? Oh, I see. That's different. It split it up for some reason. So let's undo. There we go. Let's try again. And we're rotating it. We'd have to flip it too. So, but you got the idea of what we were doing here. Is we were reorienting these triangles so they all look the same way, and then just labeling the parts, and then setting up similar triangles based on that. That was pretty much the idea. There we go. So now all three triangles are kind of lined up the same way, and we could fill in the information we needed from the parts of the triangle. And the trick was kind of keeping things straight, and which was a long leg, which was a short leg, which was a hypotenuse. That was kind of the strategy that we were using. So we had something like, I don't know, let's pick one of the problems. 8 had a 4 root 3 here. And it's oriented a little differently, but that's okay. We can do it here. This is 12 and this is x. So we set up our three triangles. We looked at our three triangles and said, okay, let's start with the smallest one, just to make life not so bad. The smallest one has a short leg, a long leg, and a hypotenuse. The short leg is x. The long leg is 4 root 3. The hypotenuse I don't know anything about, so we'll just leave it be. Let's go to the middle triangle. The middle triangle also has a short leg, a long leg, and a hypotenuse. The short leg is 4 root 3. The long leg is 12. The hypotenuse is unknown. In the large triangle, the large outer triangle, we also have a short leg, a long leg, and a hypotenuse. The short leg I don't know. The long leg I don't know. The hypotenuse I guess I could say is 12 plus x. But that really isn't going to help me very much, is it? But it doesn't matter because I only need two of the triangles to set up the proportion. I don't need all three. And very clearly these two triangles now, they both have this piece and they both have this piece. Oh, I'm sorry, that came a little dark, so let's try a different color. Let's try the blue. Okay? And they both have that piece. They have corresponding parts, and we're able to set a proportion based on that. 12 over 4 root 3 equals 4 root 3 over x. And one of the ways I could tell I had set up my proportion correctly was if I had one diagonal, I had the same value. Whether it was a numerical value or maybe x on the same diagonal or something, but on one diagonal I had the same thing twice. So now I'm cross multiply. 12x equals 4 root 3 times 4 root 3, which would be 16 times 3, or 48. We divide by 12, and I get x equals 4. It's that simple. And we're able to solve for that unknown side. And once we had that, once I know two sides of a triangle, I can always find the third side. Like in this triangle, I probably could have found this length right away. I could have used Pythagorean theorem, couldn't I? And here I could have used Pythagorean theorem to find that third side. And if I find those third sides, remembering if this is 4 root 3 and this is 12, it actually works out to 8 root 3 right there. But that hypotenuse of this triangle in this thing is really this side, 8 root 3. Now if you use Pythagorean theorem here, 4 squared plus 4 root 3 squared is 8 squared, so this third side here winds up being 8. And then we can figure out everything else that we need from that point on. We find out that this, by the way, since we found x is 4, that this side winds up being 16. And we've solved out that entire triangle using a little bit of geometric mean stuff, as we call it, or setting up these triangles, and then a little Pythagorean theorem. And that's a perfectly good way to solve these types of problems. We have the altitude to the hypotenuse of a right triangle. But there's another method that some of you may like and some of you may not like. You do not need, this method makes total sense to you and you feel like you're comfortable with it, you don't need this other method. It's not important, because this will work just fine. But if this seems a little confusing, we have a second choice that you might like better. Because we wind up with the same number on the diagonal all the time, we're always squaring. It's like 4 root 3 squared. We're squaring something. So what we've done is kind of made formulas out of it, essentially, is what goes on. This approach is more visual. It's based on looking at the picture and setting up some equations based on the picture. And the equations involve radicals, or geometric means. Basically what it comes down to is this. I have the 3 segments that make up my main right angle. The 2 legs of the big triangle, I'm going to call them A and C, and the altitude, which I'm going to call B. There's nothing magical about the letters A, B, and C. You can call them X, Y, Z, or whatever you wanted to, but I called them, for the sake of this example, A, B, C. Then I have 3 segments that go along the main hypotenuse. Okay, there's my main hypotenuse. The whole thing I'm going to call Z. Just this little piece here I'm going to call X, and just this little piece here I call Y. We know that X plus Y equals Z, the way it's set up. And if that's the case, then these relationships always exist to help us out. They're the geometric mean relationships. And we could come up with these relationships by drawing our 3 triangles if you wanted. We could actually figure out these relationships by drawing the triangles, but I'm going to save us a little time and just dive right into the formulas. The formulas are this, that the length A, okay, A, I don't want blue. A is the square root of Y times the whole thing, Z. B is the square root of X times Y. C is the square root of X times the whole thing, Z. Those relationships always hold. We call them geometric mean relationships. And like I said, we could figure these out by drawing the 3 triangles and then setting up proportions based on those triangles. It works. Works every time. Now, couple things to keep straight. This is going to be a method you want to use. Some ways to remember what's going on here. First off, the letter that's by itself here, the A, B, and C, those are these 3 segments that make up the right angle. They do not share a side with anything. Those are all by themselves. The variables that go under the radical, the YZ, the XY, or the XZ, are all collinear. Look, X and Z are on the same line, X and Y are on the same line, Y and Z are on the same line. They're all on the same line. And in every circumstance, in every one of these equations, all 3 segments we're talking about share one endpoint. A, Y, and Z all share that one endpoint, don't they? For this equation, C, X, and Z, I've got C, X, and the whole thing, Z. They all share a common endpoint. So again, it's a very visual approach to this, because you have to see the common endpoint, you got to pick the ones that are collinear, you got to do that. And for some people that's really clear and obvious. Not a lot. In fact, we used to teach it just solely this way, and a lot of people struggle with it because they just aren't visual that way. They don't see it. But for those who are, this is a really great way of doing this. It works really efficiently. Let's take a look at it in practice. Let's see how it sets up. Solve for A, B, and C. Solve for all three of those. Now, if we did not have this method, we'd have to say, okay, I do know that this whole side here is 8, right? I can figure that out. And I could set up my three triangles, and we could go ahead and solve one, and then use Pythagorean theorem. We could find all three. But I think you're going to see very quickly how efficient this method is. Because A has to be the square root of two segments that share an endpoint with A. Not this endpoint up here, but two segments that are collinear. What segments share an endpoint with A? Well, the 5 does. And which other one? The 8. So that's the square root of 40, which I can then simplify. Square root of 4, square root of 10, or 2 root 10. And that's all it takes. It's very quick. If you can understand this, if you can see these relationships, this method is very fast. Much faster than drawing triangles. Let's look at B. B, again, common endpoint's going to be here. Which two segments share that endpoint? The 3 and the 5, yeah. Can't simplify, we're done. How about C? C is the square root of which two segments? 3 and 8. Square root of 24, which would be square root of 4 times square root of 6, or 2 root 6. And just like that, I have all three solutions. I didn't have to draw a whole bunch of similar triangles. I didn't have to set up and solve proportions. I didn't have to do any of that. No Pythagorean theorem, nothing. It just all solves out. Yeah.
What if the 3 is where the C is, or the 3 is?
We would have a more complicated problem. In fact, I don't think that would even be enough information to solve it. I think we'd need more information. But that's how these set up. Now, sometimes this one would be an easy one because all the numbers just go right into the radical. Sometimes it's a little bit tougher. Notice this time that I don't have the number in the radical, but y I'm going to say is the whole side. So again, to set this up, we just set up our equations. Let's start with the 12. 12 is the square root of what two segments? Well, one that shares the endpoint is 8 times, what's the other segment? No, x only goes from here to here. It doesn't share an endpoint with 12, does it? Why? Now that's not as nice, but we can solve that. How do we solve it if my variable's under radical like that? What do I do to both sides of the equation? Square them, yeah. Just square both sides of that equation. The squared cancels the square root. 12 squared I actually have to do. That's 144 equals 8y. We divide by 8. So y is 144 divided by 8, which is 16. So this whole thing is 16, which means if this is 8 and this is 16, what's x got to be? 8. Aha. Now that I've got all that, I can solve the other two pretty easily. P would have to be the square root of which two segments that end right at that same endpoint? I've got 8 and 8, right? This is the square root of 64, which is 8. And finally, doing the third side, n is the square root of 8 and, which is the square root of 144, which is 12. It was not drawn to scale, was it? It's okay. We've solved it. So sometimes it's a little bit more work. We have to solve an equation with a variable under a radical. We can do that. That's something you've done before. Again, if you don't like this method, the alternative was to simply draw your triangles. Large triangle, middle triangle, small triangle. And if we go back to the original problem, okay, well, we can kind of see what's there. We start with the small triangle. The hypotenuse was 12, and the short leg was 8. I don't know the long leg. Okay. In the middle triangle, I didn't know anything, nothing at all. In the large outer triangle, I had that the short leg was 12, and I had the hypotenuse is y, and the long leg is n. That doesn't help me very much, but we can see here, there's our proportion. Y over 12 is 12 over 8. When I cross multiply, what do I get? I get 144 equals 8y. What's the equation I got up here? Exactly the same. Just a different way of looking at it, a different way of setting it up. That's all there is to it. And yes, we could have put the other values in here, by the way, that this is n, and then we could have put all those letters in, but I think you're getting the idea. These are different ways we can solve these types of problems. It's a little different. And then from once we have that's that length, then we could use Pythagorean theorem to solve the rest of our sides. Yeah.
Would it change if, well, 144 divided by 8 is 18, that's 6.
Oh, did I do that wrong? I'm sorry. Yeah, that would change it. Because that would be 10 then. That would change my values. My bad. That becomes 10. That does change my values a little bit. It just changes these values. So P would be the square root of 8 times 10. And this would be square root of 10 times 18. Square root of 80, which is 16 times 5, so 4 root 5. And 10 times 18 would be square root of 180. 18 times 10, or 36 times 5. So yeah, that does actually change the values. Thank you for that. This one's a little different. Solve for x, but notice it's not just x, it's kind of in an equation form, x plus 5. And again, we could do this with proportions, or we could do this with geometric means. I'll do it both ways. So let's start by doing it with proportions. Okay? With proportions, here's my small triangle. Small triangle is short leg x plus 5, long leg 12. Medium triangle is short leg 12, long leg 18. I really don't even need the outer triangle, do I? Because that's everything I'll need. So 18 over 12 is 12 over x plus 5. Now I have to be a little more careful when I cross multiply. 12 times 12 is 144. Is 18x plus 18 times 5 is 90. 50 plus 40. Yep, 90. And then we have to do a little more algebra. So what's that, 64? 54. Sorry, I can't add and subtract today for some reason. And divide by 18, and I get x is 3. So this is 3 plus 5, so the actual length there is 8. And once we know that that's 8, then I could use Pythagorean theorem to solve what else I need to solve. If I did the geometric mean method, again, here's my outer segment. The square root of this segment, x plus 5, times this segment, 18. When I square both sides, I get 144 equals 18 times x plus 5, or 144 is 18x plus 90, which should look rather familiar to us. So it really doesn't bother me which way you choose to set this up. If you like seeing the segments and setting up the square root, the geometric mean equations, that's fine. If you prefer to set up the similar triangles, that's fine. You may use either method. But I'm just showing you there's more than one method that's involved here. And you kind of have a choice as which way you want to go with that. So we do have a book assignment tonight on this stuff where you're going to be solving some more of these triangles. You're going to be setting up and solving them from the book tonight. But I do want to also continue to look at a couple other things. This is more of a challenge type problem, by the way. Don't pack up yet. We got time, don't we? 4th hour? Yeah, we got like almost 10 minutes still. So we're not nearly done yet. We're not nearly done yet. It says, is it a right triangle? If so, find the altitude to the hypotenuse. Well, again, checking to see if it's a right triangle. Little review, Pythagorean theorem. 6 squared plus 12 squared and 6 root 5 squared. We have to compare. 6 squared is easy, 36. 144. When I add those up, that gives me 180. 6 root 5 squared, maybe a little bit more work. That's 6 squared times the square root of 5 squared, or 36 times 5, which is 50 plus 30, 180. They are equal, therefore that is a right triangle. You remember doing that, right? We just got done doing that. So it's saying if that's the case, then find the length of this altitude. Okay? Now this is a definitely more complicated problem. Because when I try to set up my triangles, it's my smallest triangle, I don't know what this side is right here. I'm going to call it N right now. And the long leg is X, and the hypotenuse is 6. When I set up my middle triangle, the short leg is X. The long leg, I don't know, but I do know its relationship to N. It's 6 root 5 minus N. That's the tricky part. And the hypotenuse is 12. When I set up my large outer triangle, I know all the sides. All my sides are 6, 12, and 6 root 5. So now I have to figure out which one I want to solve for. I'm probably going to go ahead and do this. Those two correspond. These two correspond, don't they? That's the one I'm going to have to pick. So 12 over 6 root 5 equals x over 6. They're going to be similar triangles. And that's a little bit trickier, because when I cross multiply, I get 72 equals 6 root of 5. I get a feeling something isn't quite right there. I'm just getting the feeling that something isn't quite right there. Middle triangle, short leg, long leg, doesn't matter, hypotenuse. Outer triangle, short leg, long leg, hypotenuse. Yeah, that works. 6 root 5 times x. So I have to divide both sides by 6 root 5. Now here's where we start getting into trouble. 72 divided by 6 root 5. Well, the 72 over 6, that's not bad. That's going to be 12. So I get x is 12 over the square root of 5. But we can't leave things like 12 over the square root of 5. We have to rationalize that. So it's 12 root 5 over 5. And that's the length, 12 root 5 over 5. That's a more complicated problem. Now, just this process, simplifying square roots, is what I want to spend the last couple minutes talking about, because this is important. When we divide radicals, and we're going to be doing this over these next few days, when I simplify a radical, 3 over root 5, remember we rationalize that, we've talked about this, by multiplying by 1. And we express 1 in such a way so that our denominators match. Because when they match and I multiply them, the square root goes away. In the numerator, I get square root of 15. Denominator, is square root of 25, which is 5. I have to be careful when I do this process. I can't reduce something outside with something under. The 4 and the 6 does not reduce to a 2 and a 3. So I have to multiply this by root 6 over root 6. Get 4 root 6 over 6. And now I can reduce it because they're both on the outside. 2 root 6 over 3. This is not an easy process. And you're going to be given some problems today to practice this some more, because this is something that we're going to be working with. I made up a little worksheet. The other thing we're going to work on a little bit is solving equations with square roots. Now, people get bent out of shape, but it's really no different than this. 3x equals 6. How do I solve that? That's really simple. No square roots. How do I solve that? Divide both sides by 3. X is 2. So if I have x root 3 equals 6, I'm just going to divide both sides by root 3. Problem is I have to rationalize that answer. Multiplying by 1, same thing top and bottom, matching the denominator. I get 6 root 3 over 3, which is going to reduce for me. There's my solution. Or if I have n root 2 equals 5, again, same thing, divide by the square root of 2. So n is 5 over the square root of 2, which then needs to be rationalized. And that 5 and 2 do not reduce, so that's our answer. And you've done stuff like this in Algebra 1, but this is going to be a process that we're going to do a lot over the next few days. This whole dividing and rationalizing. You need to be getting used to that. Let's put our electronics away. So I've given you a little worksheet today in addition to the homework, which, by the way, I'll put up here now. But I've run off a little worksheet to just review a few of these problems. And each worksheet, by the way, it has an example on it of each type of problem too, kind of written out and shown. And we'll get your book assignment, which is not long, in this, but we have some Serious work to do with this stuff. There's no vocab tonight. 3, 4, 13 through 18, 21 through 23 in the book on that page. Plus then these few radical problems. There's like 10 of them. Number 10 is a bit of a challenge problem. A little bit tougher. But we're just going to keep bumping into everything here. We're going to keep doing the radical review. We're going to keep reviewing these topics because, again, starting in our next section, you're going to have to be solving equations like that, like x root 2 equals 8. Those will be equations you're going to have to solve.